back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this segment, we're going to talk about time travel. Not the time travel you see in the movies. No, we're not talking about Back to the Future. We're talking about science. How do physicists in the tradition of Albert Einstein, how do physicists look at the question of time travel? Is it really possible that you can go backwards in time, meet your teenage mother before you're born, and have her fall in love with you? Well, our special guest today is Professor Richard Gott of Princeton University, author of the book Time Travel in Einstein's Universe, also author of Cosmic Web, The Mysterious Architecture of the Universe, and also Welcome to the Universe. So, Richard, thank you for being on Science Fantastic.
Well, it's great to talk to you again.
So, Richard, when you were a youth, I understand that you got involved with the Westinghouse Science Fair projects. How did you get involved? What did you do? And how important is it to inspire the next generation of scientists?
Well, I did a project on metallic sodium. I was relating crystal structure of metals to space-filling networks of polyhedrons, like stacking cubes up to fill a garage, and that would correspond to a cubic pattern in a crystal structure. And I won second place in that contest. And, many years later, they asked me to be the head judge of that contest, and so I did that for about 14 years. I think it's very important because it gives teenagers an outlet for doing research in high school, and the best way to find out if you're interested in doing science research is to try it. So there's much undiscovered talent all around the country that we're trying to seed.
Yeah, I have a lot of fond memories of science projects in high school. I did one myself. When I was in high school, I got a cloud chamber and photographed antimatter, anti-electrons coming from sodium-22. And then I built my own particle accelerator, a 2.3 million electron volt betatron particle accelerator, in principle capable of producing X-rays of about 2.3 million electron volts. But anyway, let's not talk about science fair projects. Let's talk about time travel. Now, a lot of people understand that Einstein said you can't go faster than the speed of light. So, well, that's it, folks. You cannot go backwards in time because you cannot break the light barrier. However, didn't Einstein have a larger theory called general relativity, where space and time are like a fabric that can be stretched and molded? What are your thoughts about this?
Yes, he opened the way to time travel to the future in his theory of special relativity. You just needed to travel near the speed of light. You would age slowly, so when you came back to Earth, the Earth would be many, many years in the future. But in his, as you say, in his theory of general relativity from 1915, this is curved space-time. So there are some solutions to Einstein's theory of general relativity that are sufficiently twisted to allow time travel to the past. And this works like this. Magellan's crew went west-west-west around the curved surface of the Earth and returned back to Europe. Even though they were going west all the time, they came back to Europe. So these are solutions where the time traveler is going forward toward the future locally. He thinks he's going toward the future, but yet he can circle back and come back to an event that he, in his own past, to visit. So this is the solutions of Einstein's equations that allow time travel to the past.
And I understand that around 1949 or so, Einstein's next-door neighbor, Kurt Gödel at Princeton, discovered a solution of Einstein's equation whereby if the universe rotated fast enough, you could go around the rotating universe and come back before you left. Now, that's amazing, right? Time travel, right in a cosmological model of the universe.
That's absolutely right. We observe that our own universe seems to be expanding but not rotating. Gödel's universe was not expanding, but actually rotating. But the important thing was that it showed such a solution was possible. And since then we found others like wormholes and one that I found around cosmic strings that also allow you to do this.
Right, and I understand that if you have a cylinder, an infinitely long cylinder that's spinning rapidly enough, and you dance around the cylinder like dancing around a maypole, you can come back before you left.
Yes, this was a solution found by Mr. Tipler.
Yeah.
It's yes, and the same sort of thing happened with two moving cosmic strings that I found. The cosmic strings are dense threads of energy left over from the Big Bang predicted in some theories, and if they were moving rapidly enough as they passed each other, you could circle them and come back in time to before you started, as occurred in the cylinder.
Okay, now, these cosmic strings, can they be finite in length so you can build one in your garage, let's say, or do they have to be infinitely long like some of the other solutions of Einstein's equations?
Well, no, they can have a closed a loop of string. They're either like spaghetti, infinitely long, or they're like SpaghettiOs, a small loop. And the small loop can contract under its own tension and end up with the sides moving fast enough to make a time machine. And I showed that just when that was about to occur, the whole thing would be surrounded by a forming black hole. So the time travel region would be trapped inside the black hole, so you might be able to time travel around the string loop.
Okay, Richard, we have to take a short commercial break, and after the break, we're going to talk about the question of what happens if you go backwards in time and kill your parents before you're born. How can you survive such a catastrophe? Welcome back to Science Fantastic with Professor Michio Kaku. Today we're talking about time travel. Now, Richard, before the break, you mentioned that if you have cosmic strings and you go around them in a certain configuration, you can go backwards in time. Well, first of all, what is a cosmic string?
Well, we think that in the early universe we had a period of inflation with very high vacuum energy, and that is decayed to lead to the normal Big Bang solution producing a lot of particles. But one thing that can happen is it's like when snow melts, you can be left with a few snowmen. And so a cosmic string is a thin thread of high vacuum energy left over from the early inflationary beginning of the universe. And these are predicted in some theories, and we haven't found them yet, but we are looking for them.
Now, there's even a movie with Star Trek where they talk about cosmic ribbons in outer space, but of course that cosmic ribbon was inspired by cosmic strings. So once again, what is the configuration of how you would have to go around these cosmic strings in order to go backwards in time?
Well, the two cosmic strings would have to be approaching each other, and they would be passing each other like ships in the night, like the masts of two ships passing in the night. And so the thing you would have to do is to travel around them in the opposite direction to which they were passing each other, circle them as they were passing each other, and then you could get back before you started.
Now, some astronomers have actually looked for cosmic strings, right, with their telescopes, given the fact that maybe the Big Bang perhaps expanded some of these strings so that we could see these strings moving in outer space. So have people had any success at all trying to find a cosmic string?
We haven't found one yet. There was a false alarm once, but we've been looking for them. I mean, every time we see, what you would see is you'd see two images of a distant quasar And the light path coming to us from one of the images would have gone around the left side of the cosmic string, and the other image would have gone around the right side of the cosmic string, and the curved space around the cosmic string would have bent those light paths so they both came back to the Earth, and they would be equal brightness images. And so we're looking for that, but we haven't found a case of it yet. But their search is ongoing.
Okay, and as you mentioned, there's another design for a time machine coming from wormholes. Wormholes were introduced by Einstein himself around 1935, as I recall. Yeah. But I guess no one has ever found a wormhole either, right?
Well, Kip Thorne and his colleagues proposed this. You take a shortcut. You beat the speed of light, basically, by taking a shortcut in these solutions. So if you want to go to Alpha Centauri, you take a shortcut through a wormhole to get there, and if you move the wormhole mouths around appropriately, you can create a time machine. And Kip Thorne, by the way, just won the Nobel Prize for his work on LIGO, where they found colliding black holes.
And there's also the Alcubierre drive. We had Miguel Alcubierre on the radio, in fact, and he mentions that if you compress space and time in front of you, then you could leap faster than the speed of light. But of course, there's always drawbacks with that design as well, right? In fact, there's always some drawback with these designs, right?
Well, yes. His warp drive. I was actually the referee on that paper. He showed that
right?
He could make it into a time machine. So the Star Trek episodes that involved some time travel in the past to rescue the whales and things like that, they actually had some basis. If you have a warp drive, you could theoretically use it to make a time machine as well.
Right. However, there's always a catch, and he mentioned to me that the fuel necessary to drive his warp engine requires negative energy or negative matter, and we haven't seen negative matter anywhere in our universe. It would fall up rather than down, and some people doubt that it even exists at all. So what are your thoughts about all these designs that require exotic materials like negative matter, negative energy, and we've never seen negative energy before? What are your thoughts?
Well, I think I'm more optimistic. The negative energy that Kip Thorne was using in his to prop his wormhole mouths open was produced by the Casimir effect. This is a quantum effect, a vacuum state that exists between two parallel plates. And this was proposed like in 1948, but the pressure effects associated with this Casimir vacuum have actually been observed in the lab. So we've detected the Casimir vacuum, and it has a negative energy density. So it's a quantum effect. And that's what he was relying on. There's also a slight negative energy density effect around a black hole that slowly causes the black hole to evaporate. This is the Hawking radiation. So the Hartle-Hawking vacuum around the black hole has a slight negative energy density. So I think that these are not as far-fetched as people might at first think.
Now, every once in a while, someone says that they've been able to create a design for a time machine that they can put in their garage. Now, given the fact that we're talking about black holes, we're talking about tiny amounts of energy from the Casimir effect, don't you think that it's a little bit premature for these basement inventors to announce that they've created a time machine in their basement?
Yeah, absolutely. The Kip Thorne wormhole solution would weigh about 200 million solar masses. And
Is that right?
The cosmic loop of string that I was talking about, this might be, a fraction of the mass of our galaxy. So this is not something you're going to be making in your garage, but we're interested in these, the theoretical possibility for them, because to realize whether these things may be possible, we may have to learn about the laws of quantum gravity, and this is the topic of great interest. So they're a great thought experiment to explore physics in the extreme. And, of course, Einstein was talking about spaceships traveling near the speed of light and ended up with E equals mc squared, which had practical consequences.
Yes, I think so. So, in other words, I guess we should not expect any amateur inventor to come up with a time machine in their basement anytime soon. But now let's talk about the paradoxes you get if you build a time machine. If you could go backwards in time, like what Michael J. Fox did, and monkey around with the past, don't you thereby change the present? In fact, change the present in a way which is logically impossible. Like, for example, if you go backwards in time and commit suicide, how could you be alive because you just committed suicide in the past? So what are your thoughts about all the paradoxes that fuel many Hollywood science fiction movies?
Well, there are two solutions to these problems, the so-called grandmother paradox, if you killed your grandmother. The first one, the more conservative one, is that the solution has to be self-consistent. In other words, it has to be, these solutions in Einstein's theory are four-dimensional sculptures that don't change. And so if you went back in the past and you signed on board on the Titanic and you warned the captain about the iceberg, well, then he wouldn't have paid any attention to your warning.
Okay, Richard, we have to take another short commercial break. But after the break, we're going to continue with the discussion of paradoxes. Can you really meet your mother before you're born and she falls in love with you? Fantastic with Professor Michio Kaku. Once again, our special guest today is talking about time travel. Now, Richard, before the break, we talked about paradoxes in time travel. And believe it or not, serious physicists have actually looked at these paradoxes. And you mentioned two types of paradoxes. So once again, elaborate on the first category of paradoxes.
Well, the conservative solution to these paradoxes is that time traveler never changes the past. He was always part of it. So if you go back in the past, you would find history repeating itself, as you might say. You don't change the past. The second solution is the so-called many worlds theory of quantum mechanics, where there's many branching worlds, like in a railway switchyard. So there's a world where World War II never happened. And if you go back in time and you change something, let's say to avoid World War II, you would just send the universe on another parallel track, and the track where you were born, the one where World War II actually happened, that universe still exists. You've just gone off onto another track, so that there's many possible histories.
Right, and that many worlds interpretation was actually elaborated in Back to the Future, the second part 2 of Back to the Future. There was one scene, I remember quite distinctly, where Doc Brown goes to the blackboard and draws a horizontal straight line and says, that's our timeline. The past is on the left, future's on the right. And then he drew a branch where the timeline split in half. And then the question is, if you go backwards in time, you wind up on somebody else's timeline. So if you save Abraham Lincoln from being assassinated, you've just saved somebody else's Abraham Lincoln, not your own Abraham Lincoln. Now, what are your thoughts? This many world interpretation in quantum mechanics, quite a few physicists, many Nobel laureates believe in the many worlds interpretation. But what are your thoughts?
I think we simply don't know. And it's one of a time traveler could test it by changing something. I think the again, I like the self-consistent one as well, because there's Novikov has investigated that a good deal and finds out that you can always find self-consistent solutions. And even in the many worlds theory, you may have many self-consistent worlds, each of which, like parallel sheets of paper in a book, where each one of them has to make logical sense.
Right. Now, some people say that maybe we have to go to a higher theory, a quantum theory, to finally resolve the whole question. I work in something called string theory. And in string theory, we have a wormhole with radiation surrounding it. So they're potentially rather dangerous. We have graviton radiation. And string theory allows you to calculate these quantum corrections as you enter the time machine. But the question that many people ask is, will the machine blow up because of these mounting quantum effects? Well, we'll talk about that after the break. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Professor Richard Gott of Princeton University, author of the book Time Travel in Einstein's Universe. So, Richard, some people say that to finally definitively settle the question of time travel, either A, you build one, which is prohibitively expensive, or B, you get a quantum theory relativity, whereby you can calculate quantum corrections to these wormholes and cosmic strings, and then settle the question. String theory being one candidate for this theory. But what are your thoughts?
Well, what we do now is we try to find a self-consistent solution where we apply quantum mechanics in a curved space-time. This is what Stephen Hawking did with the black hole. And Li-Jing Li and I found that there is a self-consistent quantum state. It's a vacuum state called a wrapped Rindler vacuum, is the technical term, and that did not blow up when you entered the time machine. And Stephen Hawking's student, Mr. Cassidy, had found that such a solution must exist, but Li-Jing Li found the actual state that satisfied that, and it was a self-consistent solution that didn't blow up. If your solution blows up, it changes the curvature of space-time that you started with as a basis for your calculation. So you haven't succeeded in making a self-consistent calculation. So our work is certainly encouraging from that point of view. But we, of course, like to have a theory of quantum gravity, a unified theory where we could put it all together and do it in one piece.
Now, you and your student, I understand, have come up with a new theory that the universe in some sense created itself, that there is some kind of a cosmic loop, that in some sense the universe is self-creating. Now, explain that idea to our listeners, please.
Okay, so Linde had shown that the inflation could produce branching universes, so that you had like branches in a tree, and each branch would grow up to be as big as the trunk and sprout branches of its own. And we were just one of this would go on forever and make an infinite fractal tree of branching universes. But you'd say, well, where did the trunk come from? And so Li-Jing Li and I proposed that one of the branches simply curled back around and grew up to be the original trunk. So the bottom of it would look like the loop at the bottom of a number 6. And so you have a branch, imagine a branch like 1 inch in diameter, circles back around, grows up to be the trunk from which it sprouted from. And I describe all this there's a YouTube video out where I was interviewed about this called Before the Big Bang, Can the Universe Create Itself? It's episode 6, and I explain it over, of course, about an hour.
Okay, now you mentioned inflation. And inflation theory says that if our universe is a bubble of some sort, then as you pointed out, the bubble can fission into other bubbles, giving you a branching network that looks like a bubble bath. And in this bubble bath of universes can collide, or pinch off and create baby universes. And so some people think maybe that's what happened before the Big Bang. But your idea is totally different, right? You're saying that one of these bubbles basically goes into the future and becomes its own past. Is that what you're saying?
Yes, one of the great things about inflation interesting things is that you take a little tiny piece of inflating vacuum state, it'll grow up to be an enormous universe of inflating vacuum state, and made of little bitty tiny pieces that all look exactly like the original piece you started with. So if one of those little pieces was actually the piece you started with through a time loop, then the universe could bootstrap itself and be its own mother. And so this was an alternative to making the universe out of nothing. We said instead of the universe being made out of nothing, maybe it was made out of something, a little piece of itself.
Now, ultimately, science is based on things that are decidable. Religion is not decidable. Religion is based on faith. But after the break, we'll ask you a question. Can you test any of these theories? And then let's talk about extraterrestrial life in outer space as well. Is it possible that we can colonize the universe? Science Fantastic with Professor Michio Kaku. In this hour, we've been talking about time travel. Not the time travel you get in the movies. No, we're talking about time travel that we physicists actively, professionally work on. With us today is Professor Richard Gott of Princeton University. Well, Richard, I understand that you're also interested in the space program and the possibility that one day in the future we'll begin the colonization of planets. So what are your thoughts?
Well, I think that the project that we should embark on is colonizing Mars. This has a survival value to us. It's like having a lifeboat in case something happens on the Earth. Colonizing Mars would change world history. You couldn't even call it world history anymore. And so this is the project that I think we should concentrate on. And when I grew up, I went to see Neil Armstrong take off for the moon. That's a picture that I took is in the last page of the book Welcome to the Universe. And this was a terrific event. And people at that time thought that we would be on Mars by 1985. In fact, Wernher von Braun had plans to do so. And we haven't done anything toward getting humans to Mars since then. And I think it's the project that we could embark on, colonizing Mars. Don't just plant a flag there and come home. This is the project that we should concentrate on and that I've advocated for many years.
Now, some people say that Mars is, very far, very, very radioactive and very cold and doesn't have much water, doesn't have much life as so far as we can tell. But some people say that we can terraform Mars, that is, perhaps inject greenhouse gases to warm up the planet, perhaps create a network of solar satellites to beam solar power onto the polar ice caps. So what are your thoughts? Do you think it's possible that in the long term we might be able, over the decades, begin the process of turning Mars more into an Earth-like environment?
Well, Chris McKay has talked about this, and we're warming up the Earth, so we know that it's possible in principle to warm up a planet. The radiation problem, I think, has been exaggerated. People could live underground, 30 feet to 10 meters underground. We had cavemen ancestors who are quite happy, and I think that that's a solution to that problem. And you come out on the surface briefly and do your activities on the surface. The point is we could send a small group of astronauts and they would colonize Mars and be self-sufficient. And it's a great bargain, and it's in the long term, it's something we could do in the short run that might as much as double our survival chances in the long run, because we'd have 2 planetary chances instead of 1.
Now, some people say that it's practically a law of physics that one day the Earth will be destroyed. In 5 billion years, the sun's going to eat up the Earth. In hundreds of millions of years, we can expect another dinosaur-killing type asteroid. And then in the meantime, we have volcanic eruptions and ice ages and all sorts of potential catastrophes. So do you think, therefore, that it's like an insurance policy, given the fact that there's almost 100% chance that the Earth will one day be destroyed?
Yes, we know that if we stay on the Earth and never get off the Earth, we will be gone. That's true. Mm-hmm. And you know, we're living on this tiny island, this tiny blue dot in this vast universe. Are we really going to turn our back on the universe and stay here as an ultimately endangered species? And the point I keep emphasizing is that the space program is brief. It's only human spaceflight dates back to 1961, and so it's very brief in terms of human history. And so the worry we should have is that we better take advantage of this space program while we've got it, before people decide to cut off its funding, like they cut off the funding for making pyramids in ancient Egypt, and get off the planet before we quit the space program. That's the real space race.
Now, we interviewed Carl Sagan, the late Carl Sagan, and he said that we should be at least a 2-planet species because we're in the middle of a cosmic shooting gallery. We've also interviewed Steve Weinberg, Nobel laureate in physics, who says, bah, humbug, too expensive. But given the fact that costs are dropping, given the fact that Silicon Valley billionaires like Elon Musk are bankrolling a lot of these endeavors, you think that it's becoming more practical, that it's not going to bankrupt the economy, given the falling price of rockets, reusable rockets, and given the fact that, China is going to be joining the space race pretty soon with planting a flag on the moon by 2025, in fact. So what are your thoughts? Are things different than it was back in the 60s, in other words?
Well, I think China, for example, the project I would suggest to them to garner world headlines is to suddenly send a spacecraft with a person on it on a figure-8 orbit around the moon that breaks the altitude record. You don't have to go further away than Apollo 13 did. This would capture the headlines, not an orbital flight.
Okay, Richard, unfortunately, we've run out of time.